Well, welcome everybody for the second lecture of this course on Boostrap. So, just like a recap of the big picture. I kind of defined during the last lecture Bootstrap methods to be some kind of more or less rigorous methods which are useful for studying various complex systems. So when you have some systems that you cannot solve exactly, you can often formulate some kind of algebraic constraints that the system needs to satisfy, and then you can use this algebraic constraint, this notion of positivity, to prove various rigorous bounds on observables in these systems. And last time we discussed two applications. The first one was measures, so basically measure theory, and the second one was quantum mechanics, which is some kind of a non-abelian generalization of that. In the case of the measures, we could see that we want to define a measure to be a positive linear function on some space of functions, and this actually turns out to be a complete characterization of measures. That if you classify all positive linear functions, so linear functions which map positive functions, then you classify measures. And the quantum mechanics case is a non-abelian generalization of that, where instead of having a positive linear functional space of functions, you now have a positive linear functional on some C-star algebra. And we could see that this actually can be made very precise and practical. That you could use this abstract algebraic characterization of states in quantum mechanics to prove bounds and energy levels in the anharmonic oscillator and so on. So if you haven't been here, if you haven't watched the lecture, I encourage you to watch the lecture to actually see that this what sounds like an abstract nonsense actually can be made very precise and practical to prove bounds and quantities in systems of physical interest. And today, and another thing I wanted to say as a general statement is that it can often be proved that if you kind of systematically add more and more constraints into your problem, then the bounds that you get become arbitrarily sharp. That somehow this algebraic characterization is somehow complete. And in the first part of the lecture of today's lecture, we are going to see another example of that, which has to do with dynamical systems. Okay, or at least in the first part of the lecture, we are going to do dynamical systems. Then if there is still time, in the second part of the lecture, we are going to start moving towards conformal field theory, which is our ultimate goal, of course. At least my ultimate goal. But before we get there, let's study continuous dynamical systems. What is a continuous dynamical system? So it's basically it's a first order differential equation where the variable is time, and the thing which is evolving is some vector in Rn. So a continuous dynamical system. It's a map. It's a map which is it's a map from time. So time is non-negative reals to Rn. So x is a vector in Rn, which satisfies some first order differential equation. So x dot is equal to some vector function, which depends on where you are in Rn. And this is a very general class of problems because, in fact, if you have a dynamical system which is higher order in time derivatives, then you can rewrite it as a first order, essentially by trading derivatives for additional components of the vector. Right, so this is a rather general class of problems, and well, the behavior of these things can be rather complex. For example, one important feature is chaos, which is the statement that for class of such dynamical systems, if you the evolution of x as a function of time depends very strongly on the initial conditions. Right? We change the initial condition a little bit, and the evolution at far future is going to change dramatically. So the behavior of these things can be rather complex, and it's in general hopeless to try to solve it analytically, or even to try to numerically find trajectories. You would need to, if you want to know what the behavior is at very far future, you would need to specify the initial conditions to very high precision and solve your ODE to an extreme high precision. So in general, it's not really a good question to ask, what is the precise behavior of any single trajectory, but rather the kind of questions that we are interested in is to ask about long-time averages. So the kind of questions that we are interested in, the problem is to study long-time averages of quantities of observables. So what are these? How do we define long-time average? I guess it's kind of self-evident. So you start with some function phi, which is it's a function on your phase space. So I'm going to be referring to Rn as the phase space. So phi is an observable, so some real valued function in phase space, and the long-time average, which I'm going to denote as phi bar. Long-time average is this thing. Phi bar is the limit as t goes to infinity, where we average, where we integrate phi along a trajectory. So I should say this thing will depend on the initial condition. So we start our vector at some x0, and we evolve this phi. We have evolved the vector respect to time. Very simple.
Divided by time.
Sorry. Yeah. I wrote it in my notes. Yeah. So inside of it. So the idea that somehow the dominant contribution to phi, so this long-time average, comes from the regions in the phase space to which this vector is attracted to. So in general, this may be infinite. If you have a dynamical system where the vector tends to go to infinity, then this may be infinite. But we are going to focus on dynamical systems where the vector never wanders off to infinity, and no matter where you start, it stays in some compact region of Rn. And in that case, this is a well-defined quantity.
But do you need that it stays really in a compact region or an average? So there are really no large deviation far from, let's say, the typical.
Right. I guess it should. Right. So the condition that it stays in a compact region is not necessary, but. And I'll only discuss those where it stays. So many of these. Maybe the most famous example is a Lorentz system of ODEs, which is a three-dimensional dynamical system. I'll focus on a slightly simpler example today, which is the Van der Pol oscillator. Okay, so the idea is that this phi bar rises or receives the dominant contribution from regions to which this vector is attracted. And these regions these regions, this is also called an attractor. Attractor is some region in Rn which this vector tends to. And there are various examples of this thing. So there are, for example, stable equilibrium points, which are easy to detect because they just correspond to certain points where f vanishes. So stable equilibria. but much more. Okay, so these are easy to find because you just look for points where f vanishes and you study the deviation around it and decide whether it's stable or not. But more generally, there are objects which are much harder to find as a factor. So one of the simplest example is the limit cycle. We are going to see an example of that soon. And more generally, some limit manifolds. Or even attractors which are not manifolds, and these are called strange attractors. An example of such an attractor appears in this Lorentz system.
Sorry, what you're saying in the first sentence, stable equilibrium?
Stable equilibrium points. It's just a point in Rn where f vanishes and which is stable. So the vector always points towards the stable equilibrium. Okay, so that's the setup, and it turns out that there's a rather nice bootstrap method which allows you to prove bounds on these long-time averages of quantities and dynamical systems, and these bounds are provably sharp. And not only provably sharp, but actually it can be made very precise in practice, on your laptop. So you can basically compute these long-time averages using some semi-definite programming without ever solving the differential equation. Okay, so proving height, proving tight bounds, both upper and lower bounds on C bar. So what's the idea? The idea is the following. So imagine you have some observable phi. So suppose that phi is such that it's actually bounded as a function in Rn. It has a lower bound, some a minus and a plus. Say, suppose this holds. So at first sight, the idea was completely trivial. It looks like it has no chance of being powerful. But if this is true for all points in Rn, then the corresponding bounds hold also for the average, right? Because no matter where the point goes, the p will always stay bounded above and below by a minus. But if this is true, then the average is also bounded. But in general, this bound is clearly not going to be tight, because if you have some function which is say surjective on R, so if some function which takes all possible values of R, then a minus is minus infinity, a plus is plus infinity. But if you have for example, consider some polynomial like x squared, the norm of the vector squared, then clearly this is not bounded, so this bound is going to be useless. But if you have a dynamical system where the point stays in some compact region, then the norm is also bounded. Okay, so this bound is not sharp in that case. But there is a way to make it sharp by adding zero to phi bar. And how do we get zero? Well, we exploit this differential equation. So note that if you take any function which is not phi, but take any function, then the long-time average of the first time derivative of v is zero. Why is that? I mean, that's fairly obvious, but that's okay. So if you compute the long-time average, so for imagine t is very large, 0 to infinity of the first derivative of v, meaning that we evaluate this function at the trajectory. Okay, so what is this? Well, this is the same thing as 1 over p, v at v minus v 0. And well, if under assumption x stays in some bounded region, so this thing never goes to infinity. This thing is some constant. So as t goes to infinity, this goes to 0. This goes to 0 as infinity. Okay. Now we can use the differential equation to rewrite the time derivative of v as a function of x. So here, so d by dt, just using the chain rule, d by dt for arbitrary function is the same thing as x dot the nabla applied to v of x. Here's the chain rule, and now we can rewrite x dot using the differential equation. So this is the same thing as our f, which remember was the right hand side of the differential equation. So this is now a function of x dot nabla of v. Right. So what we have learned is that for any v, so for any v which is differentiable, the long time average of this quantity is 0. So this is now some function of x. So this is 0. So now this gives us somehow more space to prove upper and lower bounds of the long time average of p. Because now imagine that there exists some v such that this function, so we are interested in proving an upper bound on phi, on the long time average of phi. So imagine we can find a v such that if we add to phi this object, which we know averages to 0, so suppose we can find a v such that this is true everywhere in Rn. Well, then just by taking the long time average of this, we still get the upper bound. Right. So now the name of the game is just to scan over all the possible v's and see if we can find such a v that this thing is actually bounded from above, and find a minimum such a plus such that we can find this v. So this is going to give us the optimal upper bound on long time average. And it actually turns out that these bounds are sharp. So maybe let me write it here. So the claim is that if you maximize, let's say in Rn, but if we scan over all the initial conditions on the vector, and we compute the long time average, and then we scan over all of these things, and we look for the maximal possible long time average, then well, this is certainly going to be less than or equal to the same thing. So now we want to scan over all these v's. And so what I explained so far is this inequality that for any v, to maximize this is going to give you an upper bound on the long time on arbitrary long time average of v. And similar, to get a lower bound, we just need to flip some signs. So that now the minimum averages is certainly greater. What do we want to do now? So we want to look for any function v. We want to minimize this thing over Rn. And then we get the best possible lower bound by maximizing this bracket over where v lives in some suitable class of functions. In practice, we're going to take v to be polynomial, at least when f is polynomial.
Would you explain again that where does inequality come from?
Right. So
You start saying
so basically the inequality is that no matter what x0 is, so x0 is the initial condition. No matter what x0 is, then the long-time average is bounded by the maximum of this function, no matter what v is. Right? You pick your favorite v, and for any v, this is some function in Rn, and look for the maximum value of this function in Rn. The long-time average of this bracket can never be greater than the maximum value of this bracket in Rn. Right? Because and now the long-time average of this bracket is the same thing as the long-time average of the first term, because the second term averages to 0.
Sorry, if you don't assume that that v is bounded, if I take the max over x over Rn, I get infinite.
That's right. So for
Okay.
if you just pick a v at random, the maximum may be infinity, but you're supposed to minimize over all v's. And the point is that if the class of v's that you scan over is sufficiently large, there will certainly be v's such that this bracket this bracket is bounded. We'll see an example. Now, what's actually remarkable is that, maybe are there any questions about these inequalities?
Correctly, that you're saying that the minimum basically is from these functions which are bounded, so that the average of f dot gradient.
Can you reformulate the question?
my question. It's really my question. This is inequality. It seems like inequality suggesting this contribution of second term inside the brackets positive. I mean, it's just taken as a face value. Inequality saying that what you've added on the right hand side.
Well, no. The point is that this thing which is on the left hand side only knows about a specific trajectory, whereas this thing which is on the right hand side is the same about all of Rn. So that's somehow why you're seemingly losing information. Right? You're instead of kind of maximizing your function phi over a specific trajectory, you're maximizing function over all of Rn, which seems like a much bigger set. But it's an inequality. But what's remarkable? What's remarkable is that actually it can be proved that if you scan over something a large set of these, then these inequalities are sharp. That's not obvious at all, and maybe a little bit later I can sketch the proof of why that's the case.
A question from the Zoom.
Yeah.
So the whole key is that the V's exist with the properties above your head.
Yeah, that's right. Now.
So for what classes of problems is that true? I mean, presumably it's not true literally for every chaotic system that falls into this category we began with.
Yeah. So if f is polynomial, so f is the function that is specified in the system. So if f is polynomial, then you can also choose v to be polynomial, and if you so f has some fixed degree as a polynomial, And if you choose V to have something of a high degree, then this term is still going to have a very, very, very high degree. And you can, for any polynomial, you can always find another polynomial of higher degree, such that if you add them together, then the result is positive. Right? It's easy to fix negativity of a specific polynomial by adding to it some other polynomial of sufficiently high degree, such that at infinity is positive. So basically, as long as f is polynomial, there is always a v such that max is finite, or that min is finite. More generally, okay, I haven't really thought about it, but I would imagine that for any fixed v, there is always for any fixed f, there's in fact just because these inequalities can be made sharp. This demonstrates that for I guess any f which leads to bounded dynamics, you can always find a v which does the job.
When you say it can be made sharp, you mean that there exists a v that is the equality?
Yeah, that's right. Yeah, I mean, okay, I'm not being very careful about max versus soup and so on. So I'm not really, again, I'm not trying to prove that the v should exist. Okay, that may depend on the specific function space that you're working in, but yeah.
Yeah, I guess that was sort of the source of the question. So above you say there exists a v such that the rest of it, and yeah, for all, does that actually exist for all chaotic systems in this class that we're considering, or what is the function space, that enters into the differential equation in the first place that makes that true?
So the precise statement is that if you take v to range over all functions that have a continuous first derivative, then the inequality is sharp. So the class of function with a continuous first derivative is sufficiently large to always admit an answer.
Sorry, maybe it's a stupid question, but is there an equivalent for a discrete time map?
I would imagine it can still you should. I guess you can replace the time derivative by discrete time derivative. I think it should still be the case essentially.
If the functions are regular enough, probably it goes through, but you need to add some regularity assumption.
Yeah, I haven't thought about the discrete time threshold, but that seems like a very general. Okay, so there's a theorem which I already stated in words. Let me write it down. The inequalities are sharp if v ranges over the space of functions of the continuous first derivative in Rn, and this was proven in a paper by Pascal, Boluskin, Doering. If you want to read more about the proof, then it's in this paper. 096. I think it was physical review A.
What's the name of the last person?
Doering.
Charles Doering.
I don't know who this person is. You may, is he in the audience? Exactly.
He's quite famous.
Oh, okay, yeah. This whole subject is a little bit outside of my expertise, so I don't know all the prominent figures. I just thought it was a nice application of the Boostrap-like ideas.
So two small questions. Sharp and optimal inequalities, are these the same?
Well, it depends on what you mean. Optimal sharp means that they can. In this case, sharp means that they're equal. It could be that you may. In some other situations, it could be that the optimal bound doesn't agree with reality, so it's not an equality. So in general, I think sharp and optimal don't mean the same thing, but in this case, sharp just means they're. You just say equalities. Yeah.
The precise version is for any positive epsilon, there is a V that makes the difference smaller than epsilon. That would take care of this upper bound.
Second question. Polynomial is dense in this C1, but if it works for C1, should it work also for polynomial?
Okay, so let's do it in practice. Now we are going to implement this method. To detect fractures of dynamical systems. And we are going to assume that f is polynomial. And use a polynomial ansatz for V. Okay, so now to prove an upper bound, so we fix some quantity that we want to bound, quantity, and what we want to do is to minimize a plus. I'm just rewriting what I already wrote before in a way which is more practical. So we want to minimize a plus, which is just a number, such that there exists some b, such that a plus minus b minus this thing is non-negative for all vectors in R.
The initial hypothesis of the fact that the trajectory is in some contact is still holds for this framework or no? Otherwise, how do you check that
right.
your trajectory will?
Well, I guess if your numerical system does not satisfy this assumption, then you're not going to be able to prove any bound, at least on these that would have infinite averages. So that for those systems, this method would not be effective, would not be very useful.
Maybe if you have, for example, maps for which, I mean, the entropy of initial points that leads to some bounded motion is very large, and you have just few points that go out. So this would be large deviation, right, in the initial condition. Is there a way to like arrange the theorem in such a way that I mean you can rephrase everything in probability, right? Typical initial conditions.
Yeah, you could. That's right. You can reformulate these long-term averages as instead averages over space with respect to measures which are invariant under time evolution. That's probably different.
Okay.
Then I think the same. So this is already looking pretty practical, pretty quite implementable, right? We just need to look for a polynomial such that okay. Also imagine P is a polynomial. Are there any more questions? So P is a polynomial, P is a polynomial, then it's some polynomial. So all that you need to do is to check that polynomial which is positive. But this is still a relatively hard problem. If your polynomial has a high degree, to check whether it's positive everywhere. So instead, we're going to replace this by a relaxation of the condition, which is that the polynomial can be written as a sum of squares, and that turns out to be equivalent to the statement that the polynomial is essentially the action of some positive symmetry matrix on a vector is inner product with the same vector. So it's not true. So in one dimension, a real polynomial is positive if and only if it can be written as a sum of squares. But this is not true in more than one dimension. So in practice, this is like weakening, and it could be that we are going to lose that sharpness of the inequality. But it turns out in practice, it's really equivalent. I mean, in practice, it turns out that you don't lose anything. Nobody proved that for sum of squares, the inequalities are still sharp, but it seems to work. So suppose you have some polynomial P X, and imagine that you can write if you can write P as in this way. So B is a vector of polynomials. B is a vector where each of these B's are polynomials. And if there's just a constant matrix which is positive semi-definite, then you get a polynomial which is positive for any. So this is what we are going to use. Instead of requiring that this object is positive everywhere, we're just going to require that it can be written in this way. So we're going to add some linear constraints into our problem. The linear constraint being that A plus C minus F E is equal to just like that. Where I guess these now this vector means something slightly different. So maybe let me just use indices. Okay. Q is a symmetric real matrix. So we traded this positivity for a bunch of linear constraints. Now we are just comparing polynomials, so we can impose this for coefficient of any monomial, and we traded the positivity for positive semi-definiteness of some constant matrix Q. Okay, and finally, let's look at an example. So the group of authors, or very subgroup of the authors that I referred to who prove this theorem, they have a series of papers where they apply this to successively more and more complex systems. One of the simplest one is the oscillator that I'll describe in a second, but they also have a paper where they apply the same method to the Lorentz system of ODEs, and they actually get very tight bounds on these long-term averages. So I encourage you to look at it as well. Today, going to look at a slightly simpler example, which is two-dimensional, and it's called the Van der Waals oscillator. What is this? What is the system? Well, it looks almost like a it's some slightly nonlinear deformation of the usual harmonic oscillator. The usual harmonic oscillator can be written in this way. For example, if you interpret x as the position and y as the momentum, and these are the Hamilton equations for evolution of harmonic oscillator, and the trajectories are circles in R2. But you're going to add some nonlinearity, or Van der Waals added some nonlinearity to it, which looks as follows. So there's some parameter p. P is a parameter, and tune, and then there's some nonlinear coupling. For p we get a harmonic oscillator. And let's try to, so for p equals 0 we get a harmonic oscillator, and let's try to increase p from 0 to the positive value. But it turns out, and you can kind of easily convince yourself, homework exercise, that if p is tiny and positive, then there's a limit cycle at which is a circle of radius 2. So the limit cycle is described by this arbitrary equation. And for general positive p, there is a single limit cycle, which is some smooth deformation of the circle. I should also say that for any value of p, for any value of positive p, there's an unstable fixed point at the origin. So the expectation is that
This limit cycle
for p, sorry, for p going to 0 from the
system positive. So it's
Why equals 0?
Why 4?
That's an exercise. You can, so the way you can prove this, so first of all, you kind of want to do this more or less perturbatively. So you go to a reference frame which rotates with the period of the harmonic oscillator. So if you set p to 0, then it's just a harmonic oscillator whose is 2 pi for any rate. So you go to this reference frame. So you rewrite x as u cos t into minus t and similar to y, I guess to be minus sine plus dt cos. Okay. Now the differential equation satisfied by u and v has a very small right hand side, which is of order p, and which means that the fluctuation of u and v is tiny. So the time scale at which u and v evolve is basically 1 over p. Which means that you can kind of average you can average this over a single period, and then you can study how u squared plus v squared evolves on average over the average value of u squared plus v squared over a single period, and you find the ordinary differential equation that has a fixed point at this radius. Exercise to fill in the details. I think it's probably a good time to take the break, and after the break, we are going to go back to our favorite software, Mathematica, and look how.
Maybe there are questions. It was a break.
So the authors of the paper mentioned that they are applying this to like other systems. Do you know if the systems to which they apply the method are low dimensional or high dimensional?
I think that their ultimate motivation is to apply this to PDEs, which is like the ultimately infinite dimensional case. But in practice, they do it for for 2 and 3D. This standard model.
So it's R2, R3, and
I'm not really an expert on how practical the implementation of these things is and how it scales with the dimensional space. But as long as you can check positive semi-definiteness of large matrices, then or to implement positive semi-definite programming, then it should still work.
Long time ago, there were studies of the wonderful oscillator using non-standard dimension.
No, I didn't. That sounds.
At some point, it was in
What was the?
they use infinitesimal, so there is certain way to calculate.
I didn't notice that they would mention it. Originally, the next lecture was planned for the coming Monday, but it turns out that there's a seminar at Polytechnique by your frolic, so I wouldn't want to distract attention from the seminar by joining of our queue. So I just want to conduct a survey to see which alternatives people prefer. So the first one is the original day, so that's coming Monday. Then there are two additional Mondays, November 25th and December 2nd.
There's a problem for that Monday because of the conference on HRS.
Which one?
Yeah, this one. No,
First one.
First one. Okay, so there are multiple reasons to avoid the first option, but so you can vote for it. Okay, so do you want to check your calendars? Okay, well, maybe we can already conduct a survey. So yeah, who prefers option 1? Raise your hand.
Printing any
Yeah. Option 2. And option 3.
Option 2.
You can write on the chat. Write on the chat.
So it looks like option 2, option 2 1.
They are voting online.
They're voting online. Yeah, I just eyeballed the. Okay, anybody else online wants to express their preference between 2 and 3? Who really likes to be the winner? Okay, I think it's settled.
And so for 3, right there. No?
Well, I already said okay. People who prefer 3, if you want to mobilize your forces, now is your chance. So 3, option 3, raise your hands. It's even less than before.
So okay, so two wins. So next lecture, well, next is not the next.
Next is going to be next Friday, and then I guess the next one is will be Monday.
Okay.
Okay, now let's look at a Van der Pol oscillator.
Sorry. Is that right?
So when I tried to implement this a few days ago, it didn't quite work. So it's possible that in your favorite software, which is not Mathematica, it will work better. So there is a function Mathematica semi-definite optimization, which is not the doesn't seem to be the cutting edge of semi-definite optimization technology, unfortunately. So I encourage you to play with this yourself, maybe in some other software. But the results were sort of good enough that I am going to present them now. Oops. All right, so it's a good. We can call it bootstrapping long-time averages in the fun, therefore oscillator. Let's just save it. All right. So what is this oscillator? Well, it's x dot. So x. Let me just clean. To wake up. All right. So x dot is just y. Equations. I'm just going to rewrite the differential equations again. X dot is y, some function of x and y. So this. By the way, if you have some questions about the syntax, don't hesitate to ask. I realized in the previous lecture I was kind of writing on Mathematica pretty fast, and maybe not everybody followed all of the commands. So if you're interested, in understanding some of these commands, feel free to. Also, I'm just defining the function which is the right-hand side of the differential equation. So x dot is y, and y dot is minus x plus b. Zoom a bit more. 200. Okay. 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 There is that. Correct. Okay. Now what do we want to do now? So we want to generate these, and we are going to take v to be just a monomial. So v and an m. It's just a monomial of x and y. So, by the way, if you see any mistake I'm making, let me know as soon as possible. This is some kind of ansatz for v. So we're going to take v to be a linear combination of these monomials. We actually call this v basis. Yeah. So now we just apply the. So we want to now compute the f dot nabla, which I think is a. So if you want to enter nabla in Mathematica, you can write escape del escape. So we want to compute this, which using the chain rule is the same thing as so v basis with respect to x, and x dot is that. And now plus the same thing where we replace x by y. We replace y and x dot by y dot. Okay, so this is f dot nabla v. Maybe we can simplify it a bit. Okay, so this I'll just call this basis. Basis w. Okay, this is just like our. And now what we want to bound are objects of the following form. So we'll look at some quantity phi and take some linear combination of these basis vectors. So basis in such a way that the left-hand side is positive. So from now on, let's just pick a particular phi. Let's just pick take the norm squared of the vector. Maybe before all of this, I should have. Let's just pick b to the x squared plus y squared. Maybe we can define it as a function, so that later on we can modify this to some other function. And so now we want to write it left-hand side, so that's a plus minus b and minus sum over the basis vectors. So what do these basis vectors look like, first of all? Well, they have some degree, but you can see that when the degree is 0, then it just vanishes, and we get a first non-trivial case when the degree is 1. So in general, we want to just consider the f dot v up to some given degree for v a given degree. So let's sum up to the degree. So the degree is going to be label d, and we may as well start at 1 because at degree for degree 0 there is nothing. We're going to go from 1 to d max, and we are going to add some coefficient, which maybe you're calling it n and m. So n should go from 0 to the degree, and m is the degree minus n, right? So this, okay, so this basis is d minus n. Okay, so what's written here is the most general linear combination where b ranges over all the polynomials of total degree up to d max, sorry. Yeah. Okay. Okay, what do we do next? So we want to make sure that this thing is positive. Let me call this target. This is going to be let's call this target. This is the target for d max x and y. So let's just see that this works. For example, when we take the maximal polynomial in v to be of degree 1, then we get some combination like that. We can basically take the degree and higher and higher, and we introduce more and more of these coefficients, which we need to optimize over. And we said that the way we are going to implement that this polynomial is positive is to write it as b dot q dot b. So let's first define this q. We need to so at this point we need to decide what should be this vector of polynomials, the vector b over there. So we somehow want this vector of polynomials to be something in the general that any polynomial target can be written in this form b q b. So let's look at what kind of monomials appear. Just expand it. So the basis is going to be this vector b, and we're going to choose it to be some basis of monomial. So for example,
Or can't you just reuse the b basis?
I can do that, but I need to decide up to which degree n and m should go. Right, so I guess it should be enough if n should go from 0 to this basis will depend on d max. So when x max was 2, right, you can see that x can go, the power of x go up to d max plus 2, I think.
I think by linear form, so that's you don't want to divide by 2.
No, not necessarily, because you can also get x to the
Multiply with the degree 0.
because you can take the degree 0 from the left and the maximum degree from the right. So I think I want to take the degree from 0 to d max plus 2. Well, this should be enough. Take d to go from 0 to d. So the power of y is bounded by d max, but the power of x can be bigger by 2. But also the total sum of powers is bounded by d max plus 2. So let's take b to a to be from 0 to d max plus 2 minus b. So this should. I'm not being very systematic, but if this fails, then we are going to fix it. And we should flatten it, because if you create a two-dimensional array, then it's going to be a two-dimensional array, and instead we want to have a vector. So for example, now we have a basis, which okay, it has some things which we don't need really. For example, x to the 4 we don't really need, but it's sufficient. Like it's not a problem if the basis is slightly too big. Okay. So now let's define this Q matrix, which is going to be a table and a square array whose size is the number of basis vectors. So 1 to max, and not to the max. It should be the length of that. And then we just keep it general. Q is the entry at position A and B, but we want it to be symmetric, so let's implement symmetry in this way. Now, if A is less than B, then we're going to put QAB, and otherwise we're just going to put QBA. Now this is a symmetric array whose size is the length of the B basis. It's not too large. Okay. So now at this point we can implement the linear constraint that the left-hand side is equal to the right-hand side, because we have the target D max, and this should be equal to the B basis D max dot Q matrix D max dot B basis. Let me just put this in a module. So the module function is something I was using last time. I kind of like using it because it allows you, it's basically like an environment to which variables, so you can specify variables here, and they are internal to the module. So now the module kind of evaluates everything, where you substitute d max to be whatever the value is set here. Okay, so now this is just a polynomial in x and y, and we want to make sure this polynomial is 0, so that's equivalent to setting the coefficient of all the monomials to be 0. So we are going to do a coefficient list with respect to x. Okay, so now this is a list whose entries are the coefficients of x of this big polynomial. So they are themselves coefficients of y. So now we want to, for each entry of this list, we want to extract all the coefficients of y. I mean, maybe there's a quicker way to do it, but I'm gonna do it.
X and y both to coefficient.
Yes, maybe, yeah. Okay. There are probably some faster way of doing it, and It's gonna be probably quicker if I do it the way that I usually do it, rather than trying to understand what Rajiv just said. So yeah, I'm just going to kind of apply this function, which extracts the coefficient list with respect to y. This applies this function to every element of the list. All right. And I'm going to flatten it to just make a vector out of it. And now I'm going to set this equal to 0 and solve the system of equations for the set of q's. Okay, so now we are going to write the q, a, b, which are the variables that we are trying to solve for. But I just need them to be symmetric, so I guess I can start B to B from A. Now it's an undetermined system, so not all q's are going to be fixed by this linear system. Okay. Oh, it's not a valid variable. Oh, it's because I didn't fly that problem. Okay. Hmm. Okay, so now this module now implements the linear constraint. It's solved for some entries of the Q matrix in terms of A plus and the coefficients that appear in B, and the entries, some other entries of the matrix. So let's actually define a function which does this. Here I extract, let's say, Q solution D max. Okay, and well, I don't think it's going to take too long, but just in case it does, let's save the solution every time we compute it, so we don't have to recompute solution every time. The reason I'm putting this one, so this is like the first solution. Mathematica, whenever you're solving a system of equations, Mathematica is going to spit out a list, which is the set of all possible solutions. In this case, there is only one solution, but so it's like a list with one entry, but I'm just taking this one to take care of this. Let's just see that this works. It solves it for 20 degrees. Okay, very good. So we are almost there. And when I was trying this, I realized that Mathematica implements semi-definite optimization. So let's look at this function. It doesn't work super well, but it gives us some crude answer. So what does this function do? We are interested in this in this case. So it's a function that takes two arguments. The first argument is a vector c. Ah, yes. So the first argument is a vector c, and the function tries to find a vector x of the same length as the vector of c, such that this quantity c dot x is minimized, subject to some constraints on the vector x. And what are the constraints on the vector x? Well, they are contained by these matrices. So you have matrices a0 up to ak, where k is the length of vector c and also vector x. The constraint is that this linear combination of matrices A with coefficients x is positive semi-definite. This is exactly what we need, because so the variables that we are trying to solve for are the remaining q's that we didn't solve for, and the a plus and c, and this target function is a linear function of all of these variables. So that let's define a variable list. So variables at d max is what? Well, it's one variable that we are trying to solve for is a plus. So that's a list of one element. Then we are trying to solve for these c's. So we're going to put a table So these are other variables that you're trying to solve for. And finally, we are trying to solve for the queues which do not we are trying to solve for the queues which do not appear in the queue solution. We're trying to solve for the queues which appear on the right hand side. Yes. So what are they? Let's look at all of the entries of the queue solution, but let's only look at the right hand side of the assignments. So these are the right hand side of the assignment, and in here we want to find all of the queues. So everything that obeys the pattern Q A. So this is just a pattern which applies to true whenever the function cases finds something of this form where A and B are arbitrary. And then we put this option infinity, which means it kind of scans over all the levels of this list. So I think this should. So this function outputs all of the queues which appear on the right hand side of the assignment. These are the queues that we also need to solve for in the submitted main program. So I believe these are the variables we need to solve for, and that's the vector x in the summative optimization. This makes sense. Okay, so for dmax equal to 2, we get some list of variables that we are trying to solve for, and all of the other queues are determined in terms of these variables. So now we need to build the input to this function summative optimization. So C is precisely variables, if I remember correct. Minimize vector x. Oh, sorry. What's happening here? What you're trying to minimize? You're trying to minimize is a plus. So the vector C is the vector such if we take an inner product of C with variables, you get a plus. So that's the vector whose first entry is 1, and all of the other entries are 0, because a plus is the first variable. So C vector, which will be the input of the functions in the optimization, is a vector that starts with 1, and then the rest is 0. So it's constant array, which is a vector whose all entries are 0, whose length is the length of this function variables minus 1, right? Because the length of variables also includes a plus. So this is the C vector. So it's just a vector whose first entry is 1, all of the others are 0, and that is the direct length. So that deals with the C, and now we need to build this vector of matrices. Okay, so a matrix vector. So let's look at this. The first entry is a0, so this is the constant term, which we get when we set all of our unknown variables to 0. So let's do that. First we should. What is this matrix? We have a Q matrix for some Emacs. That looks like that. And in this Q matrix, we want to implement the Q solution. So this just implements the equation there. Okay, so now we have this matrix that should be positive semi-definite, and we need to write this as a linear combination of the variables that we are trying to solve for. It's a linear function. It's an affine function of these variables. For example, if you look at this matrix and you look at the coefficient of A plus, coefficient of A plus is just a matrix whose it's just a constant matrix. If you look at say C01, it's another matrix, and so on. So first look at a constant. Let's look at a constant term, which is when we set all of these variables to 0. Let's let's look at let's actually define just Q matrix solve. Like this. Q matrix solve is one where we put all of these replacements. And the constant term in the matrix is when we set all of the variables to 0. So we set all of the C's to 0, set all of the Q's to 0, and we also set A plus to 0. Okay, sorry, I didn't specify. Right. Oh, sorry, it should be Q matrix solve. So this is no longer a 0 matrix, and it's going to be the first entry of the A matrix vector that we are going to feed to the semi-definite optimization. Because it should be a list with one element. Yeah, so this is a list with one element whose element is the matrix. And the rest of this list is going to be a table where we scan over all of the variables. Remember, we defined a vector of variables, which are the variables that we are trying to solve for, and we are going to scan over all of them. That's what we are doing here, and we are going to compute a matrix, which is the coefficient of the variable in Q matrix solved. I really hope this is going to work, at least somewhat. Let's just see that what we get makes sense. So we have A matrix vector 2 is something horrible. And if you look at the dimensions, it's a vector of matrices. So this tells you how many matrices there are, and this tells you the dimension of the matrices. So the first entry should be the number of variables. Let's just look. So if you look at the number of variables, for 2, is 49. All right, right, because there are 49 variables, but there's also the constant term. And yeah, and the matrices are 12 by 12 because that's our basis, D basis. The length of the D basis should be 12. Yeah, so there are 50 12 by 12 matrices. So now let's cross our fingers that some of them are going to work. We can just put this in a module. So the first entry is the C vector, which is just this simple vector. and the second entry is the A matrix vector. And but remember that there is a parameter in the problem which is p. That's this parameter, which is so we need to put some value. We need to set p to be some value, and it only appears here. Okay, I think now we can try to run it and see what we get. So the output of this function should be the optimal answer for the inner product of the variables with c, which is precisely a plus. So the way we set up the problem, the minimum is precisely the a plus, which is the optimal upper bound for a given d max on the problem. We are stuck at the edge of primal feasibility. Oh, sorry, the output is not the output is the set of variables. And a plus is this first variable, because yeah, that's how we did it. So yeah, a plus is the first variable. So what we learned now, if we assume that Mathematica didn't screw anything up, then this number is an upper bound on x squared plus y squared on a long-time average of x squared plus y squared in this oscillator for the value of the parameter being 1. Now, does this make sense? Well, this is clearly quite large, so it's probably not optimal. But one way we can test this method is by decreasing the parameter. So remember that when the parameter is very, very small and positive, there's the limit cycle should be a circle of radius 2. So the long-time average of x squared plus y squared should be 4. As p tends to 0. So let's set p to be something quite small, so 1/10. Success. It's okay. This is not quite 4, but maybe that's just because we haven't used polynomials of high enough degree. So let's try to increase it. Okay, this increases. 4. Okay, it's tending to 4. You run it for 5. From 4 to 5 didn't really improve. Let's see if it improves from 5 to 6. Yeah, that's true. That's true. Yeah. Maybe we should also decrease p a little bit. I mean, I'm sure it's possible to optimize this method much more. Okay, actually, it's already pretty close to 4.
If you change sign of PP,
yeah, I wonder what happens if sign. Well, once it's going to if you change the sign of PP, it's something bad is going to happen. Probably. Well, I don't know. Maybe not. Anyway, I wouldn't trust the output of this function very much, because when you actually try to, I think when you increase the dmax, the matrix become too big and the function just doesn't work with enough precision. That actually it does the matrix that claims it's positive semi-definite is actually not positive semi-definite, which is why if you really want to make progress, you need to use a better solver. 1/100. You see, this is I think what I'm talking about. So actually, it's claiming that it matrix is positive semi-definite, but it's actually not positive semi-definite. So there's an error, and this is what I'm talking about. So Mathematica is not great at this kind of problem. But what's quite nice is that in the case when the bound is optimal, or close to optimal, then this auxiliary function the only way that the bound can be sharp is if the particle that evolves stays in the region where the function is 0. Because the function, this function is non-negative. So let's suppose that we have the optimal. Let's suppose we found the optimal A plus, so the smallest A plus for which B exists, then this is positive. And I promised to you, or some people prove that through the theorem, that for that optimal B, A plus is actually equal to the average, to the long-time average of B for some trajectory, where it's really the maximum. So the only way then this can be true is if the only way this can be true is that if the long-term average of this thing is zero. Long-term average of this is certainly zero, and long-term average of this is zero by assumption. So for the optimal D, long-term average of this is zero, but it's a non-negative function, which means that the trajectory of the particle has to stay in the region where the function actually vanishes. So if we plot this optimal function, then in general, for general point is not going to be zero, but it should know about the location of the limit cycle. It should vanish precisely where the limit cycle appears. So let's try to do that. Okay, so we define this function target. So now we need to take the solution of the semi-definite optimization. So define a function solution semi-definite, which is this vector. So it's something that depends on D max and the value of P. And now we need to take our function target and replace the unknown variables by the solution. So okay, I guess how do we do this? We want to take variables D max. Let's just I like to use these modules here. So that here's the list. I guess we want to define a replacement rule, which will allow us to replace these abstract variables in the function by the solution of the semi-definite program. So we want to do a table where we scan over variables, and we say that no, actually let's do it. Let's just scan over integers from 1 to the length of variables. And we want to set up a replacement rule where we replace the 8th variable by the 8th entry in the solution of the linear program, of the semi-definite program. Okay, yeah, so this looks good. So it replaces A plus by that. All this replacement. Ah, yes. Why is it happening? Oh, it's because I put a curly bracket. Let's define a function replacement. Like that. And now we want to use this replacement in the target. Max equal to 2. for example, X. So this is now some polynomial, which if mathematically worked correctly, then this would be a polynomial which is non-negative, and in the optimal case, the particle should stay in the region where the polynomial is 0. So let's plot the polynomial. So it's a polynomial function of two variables. I'm not sure that it's going to work unless I do this. You need to kind of replace x by x to do a workaround. And let's plot x from minus, I don't know, say minus 4 plus 4, y from minus 4 to 4. I don't know why it's taking so long. Why is it taking so long? Maybe I should. Let me just define a polynomial. I just want to make sure that the polynomial is not being recomputed every time, for every value of xx. Okay, so this is a little bit faster, but it's not very good. But also remember that for d max, our solution was not very precise because the upper bound was like 253 instead of 4. When we increased it to say 6, it was quite close to 4. So what we should see is that this function is going to be close to 0 only on a circle of radius 2. So let's see if that fits. This is a polynomial of high degree, so it's a bit hard to see the precise structure of zeros from it. But one workaround is to take a logarithm. So the logarithm is going to kill large growth, and it's going to be easier to. Logarithm is infinity when polynomial tends to 0, and otherwise it's some small number. So it's a good idea to take a logarithm if you want to detect zeros, and it's looking pretty good. There's a I don't know why there are these extra circles, but there's a circle of radius 2, more or less.
Sorry, can I ask a question? So, naively, I would have thought that to get the shape of a limit cycle, you would need to know the averages of more or less arbitrary functions phi. And now you're claiming that by studying just one function phi, you can get this result. Can you really do it for an arbitrary function phi? Like, could it be phi equals 0? Or maybe you need a function phi that is constant over the cycle?
So you need a single function which is sufficiently generic. Yeah, we could try.
Change x squared.
You probably just do x. I would say you need a function. You need a function which is. Sorry, what's that? You certainly cannot use a function which is 0 because that one doesn't know anything. But
you just change, put a cube instead of a square, for instance. You're fine. You can just redo the whole thing.
Yeah. What function should I type? X cubed. I mean x cubed. Maybe I can do x. Or I don't want to do things which are odd. Maybe even it's a bit better. Something like this. Okay, so then I need to recompute that. Okay, but now we know x is 4, so maybe I need to put a 4 here. I don't know if that's good enough.
Changed coefficients just in front of the square, so it doesn't change the degrees. But you put 10.
Yeah, that's a bit safer. I can do like this. Yeah. Oh, this one I don't have to recompute. Probably I have to clear all the Q solutions. we'll have to clear the A matrix vector. Clear the solution E. What do we expect to be the average of the squared over the circle? I guess it's x squared. It should kind of increase by a factor of 3 halves or something like that. Or it should be 6. Okay, it's pretty close to 6. And if we plot that, we still get the cycle. So again, this function is sufficiently generic that it detects all different cycles. But what I wanted to show you is what happens when we increase parameter p. The motion becomes more. It doesn't really become chaotic, but the limit cycle changes shape, and there's like no analytic formula for the limit cycle.
Most cases they go into infinity. No, not analytic.
Yeah, so now I changed this to parameter to 1. Let's look at its function. Okay, it doesn't look that great. There are various features, but basically the circle became it's kind of a diamond shape region. So let's just quickly see whether this more or less corresponds to what we expect. All of this is very crude, and if you have a better solver of some of the programming in Mathematica, then you'll be able to go to much higher precision, and you'll be able to see exactly the shape of the limit cycle. But just as a proof of concept, let's see what the limit cycles of this oscillator look like. How do we solve this? So I guess we want to do this module. So let's just literally numerically integrate this equation. Mathematica inbuilt function for that method. So we have x dot would be y dot is minus x plus p. What was it? Minus. And then we also need some initial conditions. So let's say x at 0 is x0, y at 0 is y0, and then I think what we want to say, we are solving for x and y, and we are solving in some time range from t to t max. Okay, so let's say x0 is 1, y0 is 0, the parameter p, let's first make it to be kind of small, and t max to be 50.
We have t and x of t in the right hand side.
Here.
Yeah. So in the right hand side of the equation.
Okay, I don't think I have to put it there, but
X
squared.
maybe I also need to do it here.
Yeah.
Wait. Sorry. What color was it?
Maybe you should just do x0 equal 1, not
It's
equal
not.
to.
You need to change x0 and y0 in the first line of the module to an is and not a double is.
Right. Yep. Okay, that looks better. So do I need to now take the first element of the list, define a function, and now I can maybe do a parametric plot. This function.
The function is a replacement of want to do x.
The function is replaced. Oh, right. Yeah. So parameter, I need to do x. I think I saw this example in the ME solve. Here. What's the replacement?
We do x, yeah, x.
It's xt. I need to do xt, yt, like that. Okay, nice. Okay, so you can see that the function kind of tends to limit cycle at radius 2. And let's look at the shape of the limit cycle when p is equal to 1. So it has this more like diamond kind of region, which resembles that, but it's not perfect. I think if I had more time to install some proper software, then I could make it work better. But anyway, so you can see you can kind of detect the shape of the limit cycle and put a rigorous upper bound on these long-time averages without ever solving the differential equation using this bootstrap method. That was supposed to be the punchline, and I think it's a good time to stop.